So I will be recording this part of the session. If anybody has any objections with the recording, please say so now. Okay, so where are we at right now? We are in unit 3 that has to do with the fundamentals of electrical circuits. And we've gone through Ohm's law, okay? We've gone through Ohm's law. And let's just do that because we didn't do that, and let's have that recorded for posterity. Everybody turn on your cameras. Everybody turn on your cameras, quickly. Quickly turn on your cameras and microphones. Okay. Quickly turn on your cameras and microphones, cameras and microphones, cameras and microphones. Everybody. Everybody, let's do this. Let's do this, and let's do this quickly so we can, and this is being recorded so you can watch this. And what if I said we were going to do something else? I mean, Jorge's like, yes, please, let us begin. Let us begin. I haven't even said if we're going to do that or not. And some people are like, yes. Okay, good. This is turning into, okay, so everybody, 1, 2, 3, Om. Perfect. That makes my day, and I hope it makes for a good start for your week. Okay, good. So switch over back. So we've been talking about electrical circuits. So first we talked about Ohm's law, which is basically the fundamentals for the analysis of circuits. Then we talked about Kirchhoff's laws, which are basically two laws that have to do with voltage and current in circuits. So Kirchhoff's first law, the Kirchhoff's current law, that has to do with the conservation of current. The currents that go into a node have to be equal to the currents that go out of a node, or the total current algebraically is equal to 0. Next, we saw the second law, which is Kirchhoff's voltage law, which basically says that the voltage drops along a mesh or a loop have to be equal to 0, meaning that the energy that's provided has to be equal to the energy that's absorbed, or the law of conservation of energy. And we saw that using Ohm's law combined with Kirchhoff's laws, and also combined with what we know up to this point regarding series and parallel connections, we can do circuit analysis. Now, in the end, why do we do circuit analysis? We do circuit analysis to see how a circuit behaves and to find the specific values of voltages and currents in a circuit with different components. So there are a series of methods or methodologies to do circuit analysis. Now, in this course, we're going to briefly cover 3 of them. Why do I say briefly? Because again, you guys are going to take an industrial electronics course next semester where you're going to go deeper into these analysis methods. So I would say that the purpose of this course is for you guys to know them. Okay, I don't expect for you guys to really go deep into many different situations or analyses of these. That's for next semester, but we need to know them. Okay, so it's basically 3 circuit analysis methods that we're going to be seeing, and they're based on these laws or properties of circuits that we've been talking to up to this point. So the first one that we're going to talk about is what's called mesh analysis. I love to say that word, mesh. It's a mesh or meshes, mesh or meshes. Remembering that in a circuit, we're going to have loops. Remember, this is a question in the exam, remember. In a circuit, we're going to have loops. A loop is going to be a closed path where current is going to flow. So for example, this is one loop. We're going to have another loop here, for example. I'm going to call this loop 2. We're going to have another loop here. It's a path, a closed path where current can flow, where none of the elements are repeated. So those are loops in a circuit. Now, does somebody remember what was the difference with a mesh? So that was a loop. What was the difference with a mesh?
Yeah, that it only had one loop, right, inside or something like that?
Kind of like that. Camina, you're on the right track. So a mesh only has one loop within it, right? So that's correct. So a mesh doesn't have more than one loop inside it. So for example, L2 that I marked here, this is a mesh because it doesn't have any other loops in it. I'm going to call this mesh 1. And what I call loop 3 is another mesh. Loop 1 is not a mesh, okay? Why is it not a mesh? Because it contains other loops within it, okay? So I'm going to clear, so that's basically kind of the overview of the, of just of those concepts that we had already seen. So the first circuit analysis method that we're going to see is the circuit analysis method called the mesh analysis, which is basically based on defining these meshes in a circuit. So we're going to be doing this example, and we're going to be using this example for the 3 analysis methods that we're going to be using. So we should, basically what we're going to do is that we're going to take this circuit as an example, and we're going to find the values or solve the circuit in 3 different ways, and we should get the same results or congruent results. And the first way we're going to do it is using mesh analysis. Now, for mesh analysis, there are certain steps that we're going to follow. First, we're going to identify the meshes in the circuit. So I think we already stated that this circuit has 2 meshes, okay? We're going to call it mesh 1 and mesh 2. Okay, it's got 2 meshes. Next, for each of the meshes that we've identified, for each of the meshes we've identified, we're going to establish what we're going to call a current loop. What does that mean? We're going to establish a current that we're going to tag with a certain name that's going to go through the mesh. By the way, and this goes back to a question that JC had made in the previous session, I believe, talking about, well, what if we establish the current in one direction or the other? Which one is correct? It doesn't matter. Why? Because we're going to establish the current or the current loop in a certain direction, and we're going to do the analysis. If the end result is that that current is positive, it means that the current is going in the direction I established. If in the end the current is negative, that just means it's going the other way around. So for each of these meshes, I'm going to define a current loop, which is basically going to be a current that's going to go around the mesh. And so for mesh 1, I'm going to establish this current I1. That, by the way, I decided, because that's the way I woke up today in the morning, let's say, that I'm going to do this clockwise. Okay, I'm positive today. I'm not going to be negative. So it's clockwise, and I establish it clockwise. For mesh 2, I'm also going to establish another current that I'm going to call I2, and I'm going to say that that one is also clockwise. Okay. Now, again, I could have said that mesh 2 was going to be counterclockwise. I could have said that if I wanted to. It wouldn't have been incorrect. The important thing is that however I establish or define the currences or the references from now on in circuit analysis, I have to be congruent with that reference throughout the whole analysis. So it isn't valid that I establish the currents one way and in the middle of the analysis say, oh, for this part, I'm going to say they go the other way. It has to be congruent throughout the whole analysis. So for this circuit, I've defined 2 meshes. I've defined 2 currents that both are going to be going clockwise. Okay. Next, what we're going to do is that we're going to use the second Kirchhoff's law, or Kirchhoff's voltage law, to establish an equation or a relationship for each, a mathematical relationship or expression for each mesh. That's going to give me a set of linear equations that once I solve them, I'm going to have the solution to the circuit elements that I need. So let's do that. Remember, if anybody has any questions, please just raise your hand or unmute your microphones and go for it. So this is the circuit that we've got here. Okay, so we're going to be talking about, we've got two meshes and we've got the currents here. Now, how are we going to be doing the analysis? Okay, so we're going to say the following. We're going to look at the first mesh. Right now I'm here in this, I'm just looking at this mesh here. And basically what we're going to be doing is that we're going to be going through Kirchhoff's voltage law throughout the mesh. And remember that in the end, the voltage drops and the voltage, all of the voltage drops, the positive and the negative ones have to be equal to 0, okay? And so what are we going to do here? First off, we've got a power supply there, if you notice. So for the power supply, we've already got a polarity. The small bar is negative and the large bar is positive. Now for the rest of the elements that don't have a polarity, we're going to establish a reference polarity according to the current loop that I defined. So this current loop is going clockwise. So if it's going clockwise, by the way, if it's going clockwise, it means, remember that the loop is going throughout the whole circuit, okay? It means that for this element that I've got up here, the 10 ohm resistor, we're going to say that it's going in through the positive and out through the negative. And then we're also going to say that it's going in through the positive and out through the negative. And I'm going to establish a mathematical expression for that loop, okay? And I'm going to say the following. I'm just going to go through the loop, counting the elements and establishing their values. So I'm going to start here. What's the first element I find? I'm literally going to be going around the loop. I'm going to start here, and what's the first element I find? I find the 10-volt power supply. Is the current going, or what polarity is the current going in, through the positive or the negative?
Negative.
The negative. So since it's going through the negative, I'm going to say this is minus 10 volts. Then I'm going to continue. What's the next element I find? I find the 10 ohm resistor. What's the voltage in the 10 ohm resistor? It's going to be the resistance times the current according to Ohm's law. So it's going to be, and it's going to be plus because it's going in through the positive. So I'm going to say plus 10 ohms multiplied by I1, which is the current that's going through it. Next, I'm going to go to the 40 ohm resistor. It's going in through the positive. And here we've got something tricky. How many currents are going through or coinciding in that 40 ohm resistance? If we look at the circuit. So let me rephrase that question to give it a little bit of context. If I looked at the 10 ohm resistor, is it clear to everybody that the only current going through the 10 ohm resistor is I1? It's the only thing going through here. And in the 10 volt power supply, the only current that's going through there is I1. There's nothing else going through here. But if we go to the 40 ohm resistor, there is I1 going through, or the combination of I1 and I2. So for this resistance, the voltage is going to be the resistance, which is 40 ohms, multiplied by the combination of currents that are going through it, according to what I established. So I1 is going in through the positive, and I2 is going in through the negative. Okay. And those are all of the elements that are in the first mesh. And so since I already went through all of the elements, according to Kirchhoff's voltage law, which is the one I'm using, all of the sum of the voltages has to be equal to 0. Okay. Now, what I just did there, I've got it over here. So for mesh 1, we've established this expression here, which is the one I just obtained. And I'm going to simplify it. So I'm just going to multiply. I'm just going to multiply 10 I1 plus 40 I1 is 50 I1. 40 minus I2 is minus, oh, I'm missing a 0 there. Give me a moment. Let me correct that.
Professor, what do you
Yes.
say I1 minus I2?
Okay. If
Because
we,
the two currents are interacting with that resistor.
yes, because they're interacting with both of them for that resistor. But if you notice, JC, they're going against each other. So if I'm going to draw it with another color to mark. So I1 is going like this. You agree? Because that's how I established it. The red is I1. And I2 is going like this. You see that they're going against each other? And
Yes.
since they're going against each other, they're going to be subtracted. Now, what's the reference for that subtraction? It's going to be I1 minus I2, because right now I'm located in mesh one. The analysis is with regards to mesh one. Okay. Is that clear, JC?
Yes, thank you.
Okay. Now, erase that because now, okay. And so the equations I'm going to have here, it's going to be 50 I1 minus 40 I2 equals 10. I can simplify this and divide it by 10, and I'm going to get 5 I1 minus 4 I2 equals 1. Okay, that would be the equation for mesh 1. Okay, questions with that one before I go to mesh 2? Okay, now I'm going to erase all of this. Now I'm going to look at mesh 2, which is this one here. And I'm going to do the same thing. I'm going to establish polarities. So the small bar here is going to be negative. The large bar is going to be positive. In the case of the resistors, I'm going to say that the point where the current goes in is going to be positive and goes out is going to be negative. So this is going to be positive and this is going to be negative. By the way, this is important also. And this also goes back to JC's question. When we do these analysis, when I'm in mesh 1, I'm just looking at mesh 1. I'm just looking at what's happening in mesh 1 with those references. When I jump over to another mesh, I'm just looking at that mesh with those references that I established for that mesh and that current loop. Okay, it's important to not mix them up. Okay, once I do that, then now I'm going to look at my current, which is I2, remembering that I2 is going on a loop here. And I'm going to also start off here. I'm going to start off writing an expression for that. So I'm going to say the first thing I find here is the 20 volts, and it's going in through the positive. So it's going to be 20 volts. Then I'm going to go to the 40 ohm resistor, and notice that in the 40 ohm resistor, again, both currents are interacting. So I2 is going like this, and I1 is going like this. So they're going against each other. Now here in this case, we're going to have by Ohm's law 40 ohms. But in this case, now I'm located in mesh 2. So now the reference is going to be I2 minus I1. In the previous one, it was I1 minus I2 because I was in mesh 1. Now I'm in the other mesh with the other reference. And lastly, I've got the 20 ohm resistor where the current is going in through the positive. So I'm going to have plus 20 ohms multiplied by I2. And according to Kirchhoff's voltage law, this has to be equal to 0. Okay. And so that's what I've got here on the other side. For mesh 2, we're going to have this expression, 20 volts plus 40 I2 minus I1 plus 20 I2. We can multiply and simplify. 40 I1, 40 I2 plus 20 I2 is going to be 60. and the 20 volts, and everything multiplied by -1 is going to be 40 I1 minus 60 I2 equals 20. That's multiplying everything, adding, and leaving everything organized, because in the end we want a system of equations. We can divide by 2. We can divide by 20, I'm sorry, and we can get 2I1 minus 3I2 equals 1. And so what do we have here? In the end, what we have here is that we're going to have one equation here that's got I1 and I2, and we've got another equation here that's got I1 and I2. And in the end, we've got 2 equations with 2 variables. Okay, 2 equations with 2 variables. Okay. Questions with mesh 2 before I continue? Okay, okay, I'm going to clear this. And now we've got 2 equations with two variables. Okay, this gives us the 2x2 linear equation system. Okay. By the way, I'm not going to go here in detail as to the math to solving this. And I actually am not going to ask for, you're going to be having to do that in the exercises, by the way, but not in the exam. For the exercises, just a heads up, for the exercises that we're going to be doing on Friday, just work smart, you guys. You can Google linear equation solver, or linear system equation solver, or something like that. I'm going to share a link with you guys on Friday before we do the exercises, where you can basically input the parameters and it's going to solve the equations. I'm not gonna stay much time on that. So with the 2 equations, we solve them and we get that I1 is equal to minus 0.143 and I2 is minus 0.429. Okay, what does that minus mean? Can somebody tell me? These are going to be questions, typical questions for this exam. What does that minus mean? Anybody?
That the current was going to the other side?
Yes, correct. And so what does this mean? I said originally I said that I1 was going like this, that it was going clockwise. And I said that I2 was also going clockwise, okay? The reality is that that negative sign means that they're not going clockwise, they're actually going counterclockwise. Okay. That doesn't mean that the analysis we did was wrong. It's just stating the negative, that it's going the other way around than what we had established. And so it's important to interpret the signs. Okay.
Professor,
Yes, go ahead.
if we would have done it the other way, we would have positive
Yes.
answers.
Yes, correct, Carmina, right?
Yes.
Yeah, yes, correct, Carmina. So for example, and by the way, Carmina just brought up something that I'm going to suggest. Remember, you guys, I'm doing these exercises, I'm recording them. This comment is going to be recorded. I'm recording them. And when I ask questions, there's just about 2 or 3 people that are answering, okay? It's JC, it's Carmina, maybe Lucia, maybe Karen, maybe Mariana, and the rest of you are quiet because you're paying attention. However, it's important for you guys to do these exercises. So, Carmina, something that I would suggest is the following for everybody. Do this exercise again, but instead of placing I1 and I2 clockwise, place them counterclockwise. Oops, I did the same thing. Place them counterclockwise. Okay? And do exactly the same analysis. Do exactly the same steps I did here. And what are you going to obtain, Carmina? You're going to get exactly the same values, but you're going to get them positive. Okay? That's actually the only difference that you're going to be having with if you do the analysis the other way. Okay, so practice. That's a good practice for you guys. Do exactly the same circuit. You can even watch the video and go through it, and you're going to get the same values, but you're going to get them negative. You're going to get them multiplied by -1, which would be positive. Okay, so I recommend you guys do that. Lastly, we've got the two currents that are going through these two meshes. We've also got, we would like to know what the specific current is through this element here in the middle, which right now we've identified that current by as I3. Well, if we use node analysis, we take any of the nodes, for example, this node here or this node here. If we identify these two nodes, we know that I1 plus I2 is going to be equal to I3. And so that's going to give us the following expression, meaning that I3 is going to be 0.2886. Okay, well, actually, let me correct that. Oh, I've got a mistake here. Let me correct that quickly. Actually, the currents that are going, if we take the top node, let's take the bottom node here. Let's take this node here. Okay, there's a mistake in this equation. The result is correct, but I need to correct the equation. Okay, I'm going to correct this. What are the currents that are going into this node? It's I3 and it's I2. And what's the current that's going out of the node? And again, just to clear that up, this one is going like this. And this one is going like this. So, and this one is going like this. So the currents that are going in to the node are I2 and I3.
Wait, Professor,
Yes.
at the end, I1 is going the other way, no?
Oh, wait a minute. You're right. You're right. Give me a moment. Put this one incorrect. Thank you. Thank you for that catch, JC. Yeah. Well, I1, wait a minute. No, I1 is going like this. Okay, so I1 is going like this. It's coming out of the node. Okay, no, it was correct. I'm following the same, I'm not doing any modifications with the one there. No, it was correct. Okay. And so the currents that are going in are I2 and I3, and the current that is going out is I1. So let me correct that here. The current that is going, the currents that are going in are I2 and I3, and the current that is going out is I1. Okay. Let me just write that down here. Okay, correct that. Okay. Bad copy. So I2 and I3 are going in and I1 is going out. And from that, we get that I3 is 0.286 amps. Okay, following the convention. And so this way, we have all of the currents from each of the elements, and we've solved the circuit. And so this is an example again of mesh analysis. And so what we do is that for each of the meshes, we establish an equation, a mathematical expression using using Kirchhoff's voltage law, and we are able to get the linear system of equations. By solving the linear system of equations, we get the currents or whatever values we're looking for in the circuit. Now, with these three currents, we can find any of the rest of the values we want. We could find any of the voltages and the resistors if we wanted to, or even the power in each of the elements. Okay. Okay. Questions with this mesh analysis example before we jump to the next one? Okay. No. Okay. Now, the next type of analysis, if we've got a mesh analysis that has to do with Kirchhoff's voltage law, well, we're also going to have a node analysis method. And the node analysis method is a little bit more based on Kirchhoff's current law. Okay. And so basically what we do for the node analysis, we're going to be using the same circuit. First, we identify every node in the circuit, as well as all junctions, okay? So a node is going to be a point in the circuit where current is going to be separated. A junction is a point in the circuit where two or more elements are connected. So the difference between a node and a junction is a node, for example, this is a node. The ones I'm marking in red. And just for the purpose of this, that's the way they named them. This would be called node B and node D. These are nodes. And a junction would be like this one that we have here. And they're calling this one A, and they're calling this one C. What's the difference between a node and a junction? In the case of a junction, we've got two or more elements connected, but it isn't, the current isn't necessarily separated. In the case of a node, the current is divided between many elements. So we identify those. We identify what we call a reference node, which is going to be the node that's the zero reference measurement. In this case, we usually use the node where the negatives of the power supplies are connected, or the bottom node, depending on how the circuit is arranged. And then what we're going to be doing is define an equation for each of the nodes based on Kirchhoff's circuit law. And we're also going to get a series of equations that are going to help us solve the circuit. Let's look at how this one would look. So first, we've got the circuit. And what we're going to be doing is that we're going to be looking, right now we're going to be looking at node B, which is this one here. Node B. And so in node B, we've got a current I1. We've got I1 plus I2, according to how they're established there, equals to I3. I1 plus I2 equals, so the nodes that are going in are going out. Now, what I'm gonna, the tricky part here of the node analysis is that we're gonna represent each of these currents as a voltage. So how do we do that? I1, which is going through the 10 ohm resistor, is going to be the voltage in the 10 ohm resistor divided by the 10 ohm resistor, according to Ohm's law. How do we define the voltage? It's going to be the difference of voltages between the voltages in the junctions. So if the current is going like it's going this way, it's going to be equal to voltage A minus voltage B divided by 10 ohms. In the case of current 2, which is the one that's going through the 20 ohm resistor, can somebody, using this same logic, can somebody tell me what this voltage, this current would look like if we're looking at the 20 ohm resistor?
Is it VB minus VA divided by 20?
Okay, Lucia, good approximation, but we have to look at the voltages that are here in both extremes of this resistor. What are the two voltages that are on both sides of this resistor?
Sorry, it's VC. Yeah. VC.
Perfect. It's VC minus VB divided by 20. Now, why do I say C minus B? Because I'm going to start where the current is going in, C minus B. And lastly, what would I3 be, which is the current here in the 40 ohm resistor? Now we're looking at...
Maybe BV minus BD.
Correct.
I don't know.
Correct, Carmina? Okay. Let's do something as a practice, because a lot of you guys do this, not just you right now, but a lot of you guys do this. You usually give an answer, which in most cases is correct, by the way, and you go, well, it's this, but I don't know. I don't know. Just try to remove the I don't know. Just state it. If it isn't correct, we're going to say it's not correct, but try to eliminate the I don't know. So you don't put a doubt on your answers in general, not just here in this class. So actually that's correct, Carmina. It would be VB minus VD divided by 40. However, there's a trick here, and there's a reason why we established a reference node. There's a reason why we established a reference node, and it's to be able to do some of the calculations easier. That's basically the reason why we have a reference node. We said at the beginning that we were going to choose a node that was going to be the reference node. And in this case, the node that's going to be the reference node is going to be node D. Why do we choose a reference node? Because for all of our calculations, this node is going to be equal to 0. That's a reference node that we're going to take. So it's correct what you mentioned, Carmina, it's going to be VB minus VD, but this is actually going to be 0. I can eliminate it. And whenever I have a VD, I can say it's 0. Okay. So
Why, Professor? What are you assuming that it's a 0?
that's part of the procedure. That's part of the in the node analysis, in the node analysis method, that's part of the procedure. You're always going to choose a node, and that's going to be the 0. And let me try to explain why, JC. Remember the lab exercise that I asked you guys to do where you were measuring voltage with the little device in the simulation? Remember, JC?
Yes.
Okay. Remember that you had a positive one, which you had a red one and a black one?
Yes.
Okay, so in reality, whenever we're doing a measurement of voltage, the positive is going to be the red one. The negative is our 0 reference, is always going to be a 0 reference. So we always measure with regards to a reference when we measure voltage. And so that is taken into the node analysis method. We're always going to be measuring the voltages with regards to a reference. And that reference is going to be a node that we define. In this example, we stated that the reference node was going to be node D. We usually try to define the reference node or the 0 node as a node that's common to the most amount of elements. That way, whenever we're doing a subtraction like the one we did here, that one would be 0. We could have also done, and this is an exercise you can do, we could have also done the other way around where node B is the reference node. And that we could do the analysis, we should get to the same results with different equations. So that's part of the method, okay? I'm gonna erase this because I already have it here. And so for node B, we've got the currents first, and we convert each of the currents to their corresponding voltages, okay? Now, after we do that, we've got the equation like the one I just stated. And the other thing is that if we look at the voltages we have, and going back to JC's question, we've got an element here that's the 20 volts. And so we've got the 10 volts here. And notice that I've got VA, the two things that are in the extreme of of that element is VA and VD. So VA minus VD is going to be equal to 10. And I just said that VD is 0. And also VC minus VD is going to be equal to 20. And again, I just said that VD is 0. And so this helps us out because that means that VA equals 10 and VC equals 20. And that's useful because I can actually substitute those here and here. And in the end, I'm just going to be left with an equation that has VB. Okay, so we can do that. And we're just going to have VB. If we solve this, we're going to find that VB is equal to 80 divided by 7. Okay. 80 divided by 7 is, just so we have that reference, 80 divided by 7 is 11.42, just as a reference for that value. Let me just write it down here. 11.42 volts. And substituting this here, here, and here, and also taking these values that I already found, this one and this one, and substituting them here and here, I can actually find the values of the three currents, which are the same values of the currents we found in the previous exercise, with one exception. Notice that in the previous exercise, this current was negative. Well, yes, because in the previous exercise, if you remember, I had established a loop that was clockwise. So in the previous exercise, I2 was going this way. For this analysis, I2, I established it was going this way. So in this exercise, it's positive because it's according to the analysis I'm doing. In the previous one, it was negative because it was the I2 was going the opposite way. But both results, even though they have different signs, are congruent with the direction that the current is going, which in this case, which in this case is going counterclockwise, or from right to left. Okay. Okay. Questions with this, with the node analysis example? Again, you guys are going to be doing some. We're going to be doing some exercises on Friday to practice all of these. Okay.